quantum, what have been pleasant surprises, what have been sad surprises. With me today I have Michał from PsiQuantum, our twin brothers, I would say, from an approach point of view. He works as a quantum application software engineer, type 3, maybe we can add on to there. We also have Adam from SandboxAQ, which works on the simulation side, where he's a technical lead. And then we have Marta, who is at Zapata, located here in Toronto as well, working as a research manager, I believe, doing all things great quantum at Zapata today. So maybe to kick it off first, gonna just ask flat out, what was the most pleasant thing maybe in the last 2-3 years in quantum that you've seen come out? Maybe we'll start off with Michał.
I'm very kind of thinking very slowly. I think that one of the most pleasant things in the last couple of years is seeing how the ecosystem grows and seeing that, really a lot of companies are deciding to release their software open source, and seeing there is a lot of, I think, openness in the community. And I think it was this way, from the beginning. But it's great to see organizations such as like Unitary Fund to just like thrive in this ecosystem, and it's great to see companies like, for example, Microsoft, who recently released their quantum resource estimation software, which was closed source. They released it open source. So yeah, I think that's something I really enjoy and makes me happy to work in this field.
It's a very quantum answer. It's like nothing works, but the ecosystem is great. We're all very friendly.
Oh yes.
With each other. Maybe a follow-up for somebody else. That sounds like a great thing. Do you think that will actually change once we have something of value to actually show? Like right now, I feel we're being very open because maybe there isn't that much value in quantum resource estimation. But you're all from companies that are eventually going to try to make a profit. Maybe, Marta, what are your thoughts on what's going to happen once there's value in these tools?
I mean, I think that for sure, as Michał said, like the fact that the community is growing is great. It's great, but for sure there will be how do you say this? Let's see. I think that for sure when we will have something of value that will be like disruptive for everyone. There will be a lot of things that need to be created, like figures who are putting things into production, for example. Like once you have like the idea, then that works, but then you have to like put into production, deliver it. That's a figure that right now doesn't really exist because there's really nothing that can be kind of commercialized at this point. So for sure, like there will be even a bigger growth in terms of the types of figures that really need to be identified. I think right now, for example, if you look at the different quantum companies, there's a bunch of different figures with different titles, and they're all very kind of vague, like what they're working on. Like different titles means a bunch of different things. So I think like as the applications, as the results will be more and more exciting and actually useful, then will be like a more clear, even career path, for example. So people will also be more excited to join the industry as well.
Great. And Adam, from your favorite surprise, the thing that made you happiest in quantum?
Yeah, it's a bit tough to pick out because I honestly think the past 2-3 years have been a little tough for quantum. Was the Google quantum supremacy result 3 years ago? That might just be on the cusp.
Ours was 2 years ago.
Ours was 2 years ago. Then it must be Xanadu's quantum supremacy result. It was very exciting personally. But I would say it has been. I think to put a positive spin on it, I think we're seeing kind of playing off here. There's been a continued sort of collaborative and like kind of healthy interplay between a sort of academic and commercial mode of application, which I think would have been difficult to sustain if some of the excitement around the kind of 2020 very low interest rate environment kind of hype bubble had kept going a bit. So I think that is in some ways healthy, although perhaps a bit tough for someone who is hoping to vest in their quantum company, in the next 6 months or something, but probably better for society in the end, is maybe how I'd say.
Yeah, actually really happy you brought up the quantum supremacy announcements in general. So maybe the question for whoever wants to answer it is, do those actually matter at all? You know, I think we've had now 3, one from us, one from Google, I guess 2 from UTSC in China, one on superconducting, one on photonic. But like, do you personally care? Do you think the field should care about these at all?
So for me, I mean, I personally don't care, and the reason for that is that I just like work far enough from hardware that really appreciating the significance of that is really hard for me. And so in that sense, for me, it's like if it's not practical, then I mean I would start caring much more if it was practical. And I just like don't understand exactly what happened there. Going through some of these took me a long of time to really start even appreciating kind of what happened. At the same time, I think that it is important, and I think that it actually these are important milestones, and I think they also prove something, right? Like that you can actually prove those like kind of supremacy things. So it shows that the field is moving forward and that we are actually making progress, and I think that's very valuable. Especially, I would say that it wasn't like one-off thing, right? There are like so far there's been like, as you mentioned, like 4 of them, like 2 different types of hardware platforms. So I think that shows something, and I think it shows good progress in the field.
Maybe Adam or Marta, go right ahead.
Sure. So I think similarly, I don't really work close to hardware, but I think like the quantum advantage, quantum supremacy announcements like actually raise a question that I've been working on in the past few years of how do you even actually define that, especially from a let's say practical perspective. So we've been trying to like figure out metrics to quantify the practicality of quantum advantage, but even then, like, there have been attempts, but it's really hard. Like if you see in the literature, there's so many definitions, and even with the same name, you mean like really different things. And then even with practical quantum advantage is one possible definition. Otherwise, there are others like potential quantum advantage or robust quantum advantage, like strong, weak, like all of these things. And everyone like means a really like a specific nuanced version of it, depending on the applications or the domain where they're coming from. So I think like that's one of the questions that for me it's interesting to address. Like what do we really mean, and what is a quantum advantage regime reached, depending on what's your goal. Like if you're a company, if you're academia, if you're a hardware company, it's very different. So I think like that's maybe one of the questions that's still open for the community, that's still worth trying to get an agreement or like advancing towards a well-defined definition, similar to what you have to quantify classical computers. So it's I think that's, let's say, like the interesting part of those announcements for me.
So you said you've been thinking about this. Do you have a good definition, not maybe for the quantum supremacy, quantum computational advantage on that very esoteric mathematical problem nobody cares about, but how would you define that definitive advantage when a quantum computer can actually do something really useful better than a classical one? So
what I've been working on is in the domain of quantum generative modeling, which I think like the announcements on that end on quantum advantage, quantum supremacy have actually been like quite negative. But so and there's not been like any very exciting things in that, even though like also there was like to make any claim on that from a theoretical perspective, you're also very limited to a specific class of problems, and it's again very nuanced. On our end, what we've been proposing for practical quantum advantage for generative modeling is the capability of these models to generate new data that is a valid solution to a problem and that has a better like quality associated, where quality depends again on the problem, compared to the data you use for training. So this is like measurable, like very, like we introduced some metrics that are not, how do you say, like arbitrary, like you can actually measure them, even though there's a bunch of caveats as well on this. But like the ability of generating new solution to an optimization problem, like that is like, for example, from a practical like business perspective, something that comes out to be a good measure. Then comes with all of the challenges, but.
Some of that might be fighting words for some of our QML research team, but we'll maybe move on to Adam. Adam, you mentioned, quantum supremacy for you was something that was a positive note. We have two people that do not care that it was achieved whatsoever. So maybe if you could give a positive spin on that.
Yeah, I don't know. I don't know where we are in the advantage versus supremacy camp. I'll stick with advantage for now, but for sure. So I think they are important. I think that they're important for two reasons. In a positive way, I mean, you got to think of the perspective of someone who isn't themselves a scientist. Like if you're like an investor looking in this industry, it's a big difference in a world where quantum advantage has been demonstrated, even on a very esoteric problem, and even by a measure that's kind of ambiguous and debated. Yeah, sure, but it means that this technology actually did something palpable. And I think even reproducing that is still a very useful thing to do for the landscape. And I think it's an important technical milestone to work towards as well. Is it the same? I would think of it as analogous to some milestones in, say, AI. Like this might be analogous to maybe being able to draw a nice line between two abstract X's and O's or something. Yeah, that's not going to be practical. But the world's really different after you can do that than it is before. And you can kind of, and you see the way people talk about things is different. Of course, we would like to see more practical problems, and I think we will. I think it's also on the more negative end kind of exposed how, kind of touching on your point, how far off this is, or maybe not far off in time, we're not really sure, but how far off conceptually proving these sorts of results is from actually even identifying what kind of concrete business value you might add here from a commercial perspective. I remember reading a McKinsey report a couple years ago when they were like, oh, quantum computers are going to make it a bit faster to like optimize how much paint you have to spray over a car. And in fact, that was the best you could come up with after like, geez, like that's a bit rough, right? And even that was iffy. So like but I think this kind of incremental progress towards different and more concrete advantage results is actually very healthy from that perspective. It changes how people think about it.
So I just wanted to add a comment on this, where I think it's a useful kind of perspective on those advantage/supremacy experiments is that, okay, where we would be if they actually didn't happen. And like how much conviction we would have in this field if like for the last 5 years we knew that like there were like several groups trying to do that and like everyone failed. Right, so like if we imagine that as a contrast, then like I think it's easier to see. Well, yeah, actually they are important as you were saying, right?
Maybe something that I think it's also maybe the challenging part of this is that since again like these are pretty technical results, so trying to really understand them it's quite hard. So I think it's both sides, like it's good and bad in the sense that it can be a result that excites people and just creates hype because it's really hard to understand what it actually means. So I think like that's also another big challenge to try to communicate to investors. We're like really far from the technical side usually, like what those results actually mean, like what are the what's the value and what are all the caveats that also need to be put there. So I think like that's another big challenge in the industry in general.
So, I mean, my perspective for the last now 30 years, quantum computing has been 10 years away. And we keep on promising that to investors and to people in audiences like this. Personally, I do feel there's been a shift that somehow it feels more real. Maybe, Adam, back to you. In your view, what do we need to do in order to actually provide some real quantum advantage for real world problems? Like, what hardware do we need? What applications do we need?
Yeah, I think, well, I'll talk more abstractly. I'm going to think of it from a more commercial perspective, because I think a fully convincing case that even a fully fault-tolerant quantum computer would unambiguously provide some kind of advantage to any problem besides prime number factoring has not yet been made clear. And I think that is actually the biggest problem in the field. It's not, like yes, building this thing is hard, but even if I had a fully computer in front of me, it's really, even for things that people identify as clear use cases like electronic structure simulation, it's actually still quite ambiguous that there would be for something like drug discovery or material science, because these problems mostly involve founding ground states of algorithms that in principle you can find a classical algorithm to find. It's not clear that there would actually be a useful advantage to having a quantum computer. That's not true for RSA encryption, because we just, for some reason, decided to build our society on the fact that it's hard to factor prime numbers, which is kind of a funny irony, but like, so to me, that's the biggest challenge to solve, is like, what would we do with this thing even if it were there? I think that's in some ways more important than having it, but it's chicken and egg, because I think probably we won't be able to do it unless these things are here and people start writing actual code for them. So it is a bit of a leap of faith, in my opinion, at this point.
That RSA, just to let everyone know, my retirement plan is to steal half the Bitcoin that has been mined so far, because the RSA signature is right there in a ledger. Maybe, Marta, I don't know if you have a different opinion about the lacking of applications.
I just want to add a very funny story on this, because when I started working in quantum, this was 2019. Really the only thing I know about quantum computing at that point, other than quantum physics, which was my background, was a course that I took at university about it was exactly like principles of quantum computing, and you study all the how does it work, like the gates, like the qubits, the systems that you can use to implement this, and then a couple of algorithms, especially Shor's algorithm. And then I thought that was one example, that there was only a limited amount of time during the course to explain all the algorithms and the applications. And I thought, okay, that's the highlight. Then I go into the industry and I'm like, oh, there's no other book with exponential advantage demonstrated. And that was really, at the beginning, really shocking for me, because I was like, okay, it's not just that we need the hardware, we also need the applications, we need the algorithms, we need the software. There's much more that needs to be built than what I thought. But it was just for me, just discovering that this book that I thought existed actually didn't exist. And we are actually building that, which is also the exciting part of being in the industry.
So you're writing that book now. You got the first page done and the rest is blank?
Exactly.
Michał, any comments on this?
Yeah, so I would say that I totally agree with what Adam said. I think, we don't have many good applications, and I was part of this program founded by DARPA for quantum benchmarking, which the goal of the program is still running, is to among others find applications and provide some information about how big of a quantum computer you would actually need to do something with those applications. And oh my God, it is really hard to actually do that. So I think it is a huge challenge, but also just from being able to see some of that work from very close, I'm very hopeful about that part, and I think our understanding of what are good classes of problems for quantum computers, where we should actually look to find something, has grew tremendously in the last couple of years. And there's just plenty of really good work, but many different groups that give hints about what might be good directions, both in terms of applications and what algorithms could be used.
So I mean, maybe one thing from my side is definitely over the last 3-4 years, reading the news, I feel like every other day you see that whether it be a quantum startup or a well-established company claims they've demonstrated advantage on a real-world business problem. No. I'm going to say it ranges from annealers to whichever favorite version of your quantum hardware you take. Do you believe that's just bogus? And maybe I'll pass it right back to Michał, or is there something there?
I would say that most of the time, when I see something like that, I look at the way they put very closely at the wording of that announcement, and then I look at it and I was like, this announcement is not technically wrong, I guess, but it implies things that I don't think are true. So I'm just usually don't read any of these, and I just see the headline and it's oh, okay, another one of these, and I just skip over them and don't read them at all.
So maybe, Adam, do you think this is detrimental overall to the kind of quantum ecosystem and adding to the hype that we normally have around quantum?
Yeah, maybe, but it's sort of understandable. I mean, if I were in one of these, a lot of these are coming from fairly small startups, and there are a lot of pressure, I think. But yeah, I do kind of agree that they're mostly bogus.
What about the ones that come from very large now public companies?
I'm sure those ones are I'm sure those ones are derived from the legal obligation of those companies to maximize the value of their shares.
Anything to add, Marta?
No, I think like maybe, of course there's a caveat on those, but I think at least there might be the good intention of trying to like show some of the progress. Now, for technical people, if you go read those, then you're like, okay, what do these people mean by advantage? What do these mean by gain, or like what are they actually demonstrating, and what is even demonstrating this word doesn't even mean in this context. And as Michał say, usually like they're not technically incorrect. It's just that if you're not a technical person, that like you might perceive it in a very different way from what it actually is. So I think like there's this, try to make the advance like available to everyone, but in a way that in the end comes out to be like maybe much of a bigger deal than it actually is, because non-technical people might have difficulties in understanding the subtleties of things. And even like for me, being a technical person, like if I read an announcement on something that's like pretty far maybe from what I'm familiar with, I also can't really evaluate how big of a impact that has. So,
I mean, maybe just to follow up for you, because I felt your answer was fairly generous to these announcements. There's a finite number of people right now that have had the privilege to be educated in things quantum and actually be able to work in trying to solve this very difficult problem all three of you identified as what are the real applications for quantum computing. Do you not worry that we're just wasting many of their time working in random quantum startups with random large multinationals on problems that realistically should have never been tackled?
I mean, I don't think I would start a company out of an announcement from another company. I would try to get real information, like real technical knowledge on that. But that's also because I'm not very risk averse in general, or like super excited. So I think a lot about what I try to do. I think like for sure, like there's a risk in that, and I agree that it might be something that's not helpful in general. But I also hope that people who read, like before making a big decision like that, actually like think about it twice or even more than that.
I wanted to comment on that because I used to work at a very kind of small random startup years ago, and I think that after that startup didn't survive the harsh conditions of capitalism system, I started working at slightly more or like much more sophisticated startup, and I think it was. I mean, we didn't make any kind of huge claims. I would say that it was actually in some ways beneficial because, a couple of people that work there, they are right now working in different places and just like doing much more serious things. So in a sense, it gave us opportunity to learn a bit, to try ourselves and then fail. But eventually we got absorbed by the rest of the ecosystem, and I think this is healthy if there is the right balance. I mean, I would say that if there were 500 startups with a lot of funding that are making outrageous claims and all the things they are doing is bogus, then that's definitely not healthy. But I think the fact that you have places where small companies can start and try their luck and then fail, then that's very healthy. And I think that's one of the good things that CDL in Toronto is doing, because well, they're like providing training and providing help in trying. And like, well, the fact that out of, I don't know how many, like 30, 40, 50 startups in every batch, maybe 5 of them survives if they're lucky, then, well, I mean, that's just like how startups work. And that's just like, the risk that's built in the system. So in that sense, I think it's okay. On the other hand, well, if they just outright make crazy claims, that's a different story.
So I heard it's okay because I escaped. Maybe any comments, Adam? And maybe I'll just add one additional thing. A lot of this also leads me to kind of another question, which is there any value in actually working on NISQ hardware? A lot of what we've been talking about is fault-tolerant algos, but at Sandbox, with the work that you do, how do you feel not just about broadly these announcements, but NISQ hardware overall?
So let me first answer as SandboxAQ and then as Adam Lewis. So SandboxAQ is currently focuses on classical and quantum inspired algorithms for quantum chemistry and for systems that are sort of flavored by quantum. So this can be molecular simulation in general. It's about scaling up big, and it's not necessarily about using quantum hardware, including NISQ hardware. How do I feel about NISQ? I think NISQ is a very it hasn't lived. I think it was an interesting idea. It hasn't really shown some of the fruit I think was hopeful, but I think it's still worth looking into. Like there may be, because it just depends on how noisy and how intermediate scale we're talking about. There may be some point where there's a crossover and something useful happens, but we don't yet have a fully fault-tolerant quantum computer. And I do think that's worth looking into. If you are in a small startup right now and thinking about partnering with a multinational about an experiment on your NISQ device, I would advise you to spend some time thinking about the organizational map within the multinational you're talking about, and whether you're working on something that's of interest to the company, or if there's a small team that you're working for, which is essentially a kind of quantum startup inside the company that is themselves looking for internal momentum of some kind, and whether that aligns with your roadmap. Maybe the logo's worth it, maybe you get to do the right thing, but it is a trap I think I see a lot of these small startups fall into, is that they think they're talking to a much more powerful part of the organization than they really are.
Marta, you look like you have something to say.
No, I was just thinking, I think like as Adam said, there has been many more promises for, especially for the timeline, like of the, let's say, 5 years on NISQ that maybe hasn't really shown like the accomplishments. I do think that this was actually quite good, especially in the quantum machine learning domain. I think people really tried like variational algorithms and NISQ stuff that really just like, okay, let's try this. It seems like it might be working. So we just like try. With some intuitions, but maybe not very well motivated. And I remember like mentoring a student in maybe 2 or 3 years ago. I was just explaining, okay, we do this, we try this circuit, we do these ansatz, we put these gates, and then we train it. And then he's like, okay, why do we put these gates? I'm like, because everyone does it. Like, it's, there's reason, like mathematical reasons at least, that give a good intuition, but like, why really do we do that? It's not really clear. And I think that that's been like a whole big question in the entire team and like in the entire field. And having not seen the promises of this like approach actually be reached has opened, I think, quite a good crisis, I would say, in the field. And I attended QTML like last November, and it was really clear that where the field is going is try to give better like theoretical motivation and foundation to these approaches. So if that's something that people that maybe are more like theoretical than I am are actually able to figure out, I think that can still be promising for the NISQ approach. But there needs to be much more intuition or like much more reasons to do things in the way we're doing them. And I think like, if the crisis opens up like a whole new avenue, that's a step. So that's good.
Anything to add, Michał? If not, I got another question on maybe.
Oh, absolutely. I think that from my perspective, I was really hopeful about the VQAs and NISQ, and I really like VQAs. I like heuristic algorithms in general, and like VQAs are, I like them. Spend a lot of time working on them. However, at this stage, I just haven't seen them working, and I'm a little bit hopeful that like maybe there are like some avenues, but I think there is imbalance in how much time the community spends on the VQAs versus how much time it spends on kind of fault-tolerant algorithms. And I can talk very long, kind of what are some different nuances here. But my point is that there are like so many challenges in the fault-tolerant algorithms, and as we mentioned before, there's this situation that like, hey, even if we had this fault-tolerant machine in front of ourselves, like we wouldn't know what to do with that because we are not sure what the applications are. And when it turns out to actually writing out this algorithm that everyone knows, I don't know, like QP or something, if you really go into the details, there's like very few people in the world that can actually write it gate by gate as something executable. And we just need a lot of progress in that part. So, I mean, my personal hope is that NISC things will work out, but I just don't count on it. It would be nice if they did, but it doesn't seem so.
What about quantum annealing? Do you see any value in working on that approach?
Pass.
Okay. Adam?
Same answer for NISC. It's like, I don't think, it's been around a while. We haven't seen some of the results. There's some, cases where there's a cloud interface which may or may not be sending your result to a random number generator. But I do think it's worth working on kind of in a semi-academic way. I think there's some problems that you could imagine this working out for if the annealers became, it's almost like a parallel research line. The line of research you're building bigger annealers isn't going to turn into a fault-tolerant quantum computer. It's like a separate device. So yeah, I think there is some value. It could work.
So I mean, maybe a similar foil to me has been recently with all the excitement about like the Rydberg atom machines, in general, the quantum analog simulator type of approach. Just wondering if you have any different thoughts that are uniquely different than NISC and quantum annealers for that side.
I'm not actually technically familiar with that. To comment on that separately from annealing.
I saw Marta and Michał nodding. I don't know if you guys have comments.
I mean, my only comment I think for this is that I think those like neutral atoms, etc. There are like some paradigms that they didn't have time to prove themselves yet. So I think that's why I'm kind of more hopeful about that than annealing, because people have been working on annealing for a lot of time and like it doesn't work as expected. But for those approaches, I think we just haven't spent enough time on them yet to say one way or another. So I'm a bit more hopeful for that reason.
Awesome. Now that we crushed the hopes of all the young people in the room, maybe we can ask if there are any questions from anybody here. Catalina has a microphone right back there.
Do you think that like quantum computing might burst akin to the dot-com bubble that happened in the early 2000s?
Who wants to take the quantum winner question? Adam.
Well, I think it won't because it kind of has already. So like, it hasn't been quite as dramatic a burst because partly there wasn't so much investment writing in the first place. But I do think things are definitely cooled off a lot compared to where they were, partly because it costs money to borrow money now. So like in 2020 it didn't. So it changes how investors think.
Actually, question to Zapata. So what's happening there? You guys scaled down quite a bit, if I understand correctly, your quantum team. At the same time, you're partnering with DUF, it seems. Maybe you could enlighten us a little bit.
I mean, there is definitely a big focus on AI right now, which we have always actually been doing. Like I started working in the company in 2019, and I was already working on generative modeling. Of course, like generative AI these days is at a scale that is very different from the quantum generative models that you do. So like there is a lot of work to do there, but that's something that we have been working on a lot. But there's still like the quantum component in the company, because that's the quantum core that has been developed from the very beginning. So all the applications, like again, quantum machine learning, that's still there. quantum benchmarking, research estimation. That's still there. That's still been ongoing, and so that's what we've been working on. It's still like a range. Maybe like there's a larger part working on generative AI at this point. So that's it.
I was single. Okay. Anyway, I was wondering what your thoughts were on if you're familiar with cat qubits. Recent stuff coming out of Alice and Bob.
Happy to say. So I'm going to say, in general, there's really unique ways of encoding qubits onto more complex systems. So you might have heard of cat qubits, you might have heard of GKP qubits, and if you like Alice and Bob, there's a great Canadian company called Nord Quantique in Quebec that's doing things that are similar, maybe slightly more complex. Our friends at Amazon actually published a really extensive paper on this type of approach. It's all very exciting. What I'm going to say, just like every other modality, there are unique challenges to it. So it's not you get a free lunch. Everybody has it, maybe not equally hard, but very hard path to fault tolerance. It's just where it's difficult is different. And the really exciting thing about cat qubits is that you pay some initial price up front to build a more complex system that gives you advantages down the line, potentially, whether it be in error correction and error resistance. Xanadu is very much like that as well, where the qubits that we're building for our fault tolerant system are GKP qubits. You can actually get them from breeding cat states, so sometimes we refer to them as kittens. But these are very hard to make, but once you make them, your life becomes a lot easier. And in fact, folks that are working on superconducting approaches, they still need to build more complex states to implement fault tolerance in a universal gate set. So they'll have to pay that price down the line at some point as well. But yeah, great work. And maybe, I don't know if somebody wants to just comment in general on the work that's been happening in error correcting codes and maybe the excitement there.
A lot of good progress lately. Yes.
Okay, awesome.
No. I'm not error correction person, and I roughly understand the topic. But I would say it's great to see that there is definitely a lot of new results recently, and a lot of new kind of error correction codes being explored. From what I heard from people actually doing error correction, they've been definitely very excited in the last kind of 2 years with what is being explored. So it feels to me that we will see. There's like the mainstream thing was, I think, just like surface codes, and now it's just. There's like so many more opportunities and so many things for people to explore as like more people start looking into that. So I really hope we'll find more and more kind of more efficient ways to do error correction. So yeah.
Great.
Speaking about different qubit types, as well as about things that may have worked out or not worked out, there's the topological qubits. What's your opinion on where things stand there? Is that actually starting to work or not? What do you think?
I mean, as far as I know, no one knows. I mean, Microsoft is very, doesn't talk much about it. The one thing I noticed is that they actually recently started talking again about their topological qubits, because I think for like a year or two there was like nothing there. But I don't know. It was like, there's like, I think nothing very serious published recently on the topic, so it's hard to say.
Anybody else want to wager a comment?
I've just reinforced that. It's strongly associated with Microsoft, and they have not said much about it lately, so it's sort of hard to say. I'm not familiar with it, if there is. There could be.
We have 2 more questions here in the audience.
Okay. In the early days of neural networks, yeah, in the early days of neural networks, people justified their modeling by mimicking our brain. A natural question would be if in today quantum computing can be also justified by mimicking the brain and doing neuroscience this way, so both ways.
So close to my quantum consciousness question. I was saying, we're going to start with Marta.
I mean, that's a very interesting question. I think like probably the way I see it is the motivation for quantum computing is not so. I don't think it's so much in our brain, but like in like physics in general, like in matter in general. So like which is not what I think, which is what Feynman suggested. So at the very beginning. So as an original motivation of like quantum computing, you can model quantum systems like that. Now, if the brain works at a quantum level, that I don't know, might be, but yeah, I don't know. I don't usually have like I don't think I have a good opinion on that. But for sure, like at least like for the particle systems or like quantum matter, like that's a good motivation. It's in a sense it's similar, but it's maybe not. It didn't start from like the brain modeling, but maybe from like the actual nature of like physical system. So that's maybe the closest thing I would say.
Yeah. So on the side of like on the side of the neuroscience, like the brain is probably, in my opinion, not a quantum computer, because it's basically just too damp and big and wet, roughly, and hot. So like there, and also because there's been no, you would expect to see correlations between neurons and so forth that would be explained by Bell type results, which I think has not been a result that's reported. So although I wouldn't say it's completely impossible, I would personally view it as vanishingly unlikely that the brain maintains quantum coherence. I could imagine that building neural network modalities that out of qubits that are somehow inspired by the brain in a similar way as classical neural networks are, but also getting some extra advantage out of quantum coherence could be a promising way to make QML work. But that's about as far as I am aware about that path, basically.
Yeah.
Maybe if you're interested in this, there are people looking at quantum biology. It's an area that people are starting to try to understand. Are there systems that are biological that rely on quantum? There's been one or two that have been identified, but definitely like the at least fermionic superposition and entanglement in the brain is probably not going to happen. But there are some folks from the University of Calgary that shown that axons can be waveguides for light. And again, they're not proposing anything beyond that, but there is some research happening. One more question I heard.
One last question. Can you hear me?
You promised Hello. It would be.
Okay. I guess I need to.
I'm just going to say you promised that it would be controversial.
Short question.
So it better be controversial.
No. It's not going to be. So I mean, you guys are the investors in the field, and I've been hearing that there's no actual business value that can be capitalized as of now, at least. No. Okay, you're agreeing with me.
Go
okay.
on.
So I just want to hear your opinion about. So the reason why we're still investing in the field, is it because we think that we will have some like proper setup that can solve like current binary problems that we're having more faster than today's computers, or there will be like problems that cannot be represented in binary way, or are we just investing in because that we can and it's exciting to play with qubits? Like, what is your thought about those?
Okay, so first thing, regarding business value, I think there is, so like that's the first thing he said. I think there is business value in kind of for enterprise companies to actually look into quantum computing right now, and I think the value is that if you don't look into it right now and you don't learn the technology, then you will have much harder time learning it down when it's actually available. And whether, there's a question of timing, but I think it's worth learning emerging technology as it emerges, because you might be late when it's actually out there, and you are way behind everyone else. And that's what I heard from business people in those enterprises. That happened for some of them with AI, for example, right? And machine learning. They're just like, that's like, there's nothing there. And then they were behind the competition. So there, in that sense, there is some business value in, investing your time into quantum computing as an, business. Beyond that, they don't work yet. So yeah, sure. To the other question, like this kind of the second part. Well, I think that there is a promise that those machines will be actually able to solve the problems that are impossible to solve using current kind of classical hardware because of scaling. And no matter how big classical computer you build and like how smart you are about the algorithms, then like certain problems will be just beyond our capabilities. And I think there's convincing math that tells us that with quantum computers you can get, to solve those problems. So I think there is like little doubt that 50 years from now we'll be actually able to do that with quantum computers. So a lot of that I think is more of a question of the timing of, is it the right time to invest? Are we close enough that like it makes sense or not? You can have your opinion on that, like everyone has. But I think most of the people agree that those applications are definitely there. We just don't know exactly what they are. I think if we didn't have Shor's algorithm and factoring thing, then which is a proof that some applications exist. It would be much harder, but with this one there is definitely interest.
Maybe I'll just add one quick comment. There's other algorithms that don't have that exponential speed up, and there's reason to believe that without more than a quadratic speed up, you'll have a tough time with overheads. But I'd say the work that's being done on quantum architectures and quantum error correction has the possibility to move that forward as well. And the final thing I always think about too is like, if one of these guys did figure out something to do with a quantum computer that could make a ton of money, they would still be sitting here telling you that the only thing they could do is Shor's, and they'd be waiting for that fault-tolerant quantum computer to actually appear. So for a lot of companies, it's also knowing that there is a really binary transformative event coming down the line, and they know that today they can invest very little to actually de-risk a very large moonshot risk that's coming for them in the near future. Not sure if anyone has any final comments they want to add. Adam?
Yeah, I do. So I did want to say yes. Like, I didn't mean to say that there was no business value in quantum computing. So there is definitely some business value, even in the world where it's only Shor's, which I think is not going to be true, but could conceivably be true.
You're not getting your hands on my Bitcoin, Adam.
Yeah. There's people right now in like creepy black site labs saving all the information they possibly can to a giant tape drive because they know they'll be able to read it in 10, 15, 25, who knows, years, and that will be valuable information. So there is definitely some value, even if it's just figuring out, senators' emails from 1985. But like, in addition, I like thinking the point you raise is interesting. Is like, are there qualitatively new problems that people don't care about yet because they can't solve them? Almost certainly. One that I can think of is time-dependent quantum chemistry. This is something that like people basically just don't do because no one's really found a reason to. But if you really need to resolve like a coherent quantum state moving back and forth through something and really track the entanglement, that would only happen in like a femtosecond scale in like a real quantum chemistry world. That is definitely an exponential problem. And a quantum computer most likely could solve it better. It's just hard connecting that to a practical value in chemistry. But if we could do it, it's likely that new drug modalities would eventually be invented that relied on that ability. So I think you're very insightful there to say that there's stuff we haven't thought of. There's like unknown unknowns that probably will carry dramatic value.
Awesome. Let's thank our panelists one last time. They'll be available and collecting resumes for all the job openings that they have, and I'll give out their personal cell phone numbers as well at the end of the session if you're interested. Absolutely. All right, with that, I believe we have a thank you dinner.
Before we go to the thank yous, do we have any questions from the stream?
Yeah, there was actually one, if we have some time for that, from our very own Guillermo. He's chilling in the chat at home. What do you think would happen if a classical algorithm for factoring was found? Do you think it would significantly affect the quantum industry? So, like, it seems like factoring is like currently the most front-runner application that might significantly impact the world. So what would happen if a classical algorithm came about?
I mean, I don't know. Isn't it like proof that that's not, it's like, isn't it one of those situations where if there is a factoring algorithm that can do that, then like P equals NP or something like that, or not? And anyone knows?
That's people in the chat are saying that pretty much.
Okay.
Yeah.
You know what? I at the ending dinner, I'm pretty sure folks from upstairs are coming down, and it's full of quantum information theorists, and they'll be able to explain the complexity theory. I actually have I'm not going to share if it's a nightmare or a dream, but that the day that we create a fault-tolerant quantum computer, the Church-Turing hypothesis or conjecture is proven true, which is that a classical computer can simulate any physical system, including quantum. And that day, some kid in their basement proves, hey, actually I can simulate your fault-tolerant quantum computer perfectly on my laptop, and then we can all just go home and have a fantastic time.
It's already in Kit Hive's desk, in one of the drawers there's a proof.
Exactly.
So I don't want to.
Go ahead.
If that happened, that would mean that all the cryptography almost all the cryptography currently in place would suddenly not matter, because someone with their laptop could break it, and you would have bigger problems, I think, than that the quantum computing industry maybe wasn't as long-term an investment. There.
All right. Then with that, Catalina, dinner time? Dinner time. Thank you so much, everybody. And
Thank you.
Thanks.